Hi there. Welcome back to the formulaic approach. Now in this video, we are going to be discussing kinematics, and basically we want to start from the scratch. So if you are someone that doesn't know anything about kinematics, motion, this video is for you. And if you already know some things and you just want to advance, say for example, you are doing A-level courses and you want to do this, I still enjoy you to watch this video. Here's the reason. I'm going to take it from the scratch to advanced level. So for O level and A level, this video still works for you, because my student prepared some questions from O level and A level, so they are going to help you, and they are on different aspects of this kinematics. We're going to consider the horizontal motion, vertical motion, circular motion. No, we've done circular motion. So vertical motion, projectile motion. And we're going to solve questions, many questions on each of those levels. So this video is going to be long, but I enjoy you to stick with me from the beginning to the end. God helping us, I promise you that you are going to learn a lot. God helping us. Amen. Now let's go on. So now first, what is mechanics? Mechanics is basically the aspect of physics that talks about what forces do to masses, okay? All right, the impact of force on masses, and the many things that are associated with masses. That's what this guy mechanics basically deals with, So, but in this case, we are dealing with, and the mechanics itself is divided into three aspects, okay? And we are dealing with only the kinematics today. Kinematics is the aspect of this mechanics that deals with, now, mechanics has forces acting on masses, but in this aspect we are dealing with just the motion of bodies without the influence of the forces, without considering the force that is causing the body to move at all, okay? But of course, keep in mind that mechanics deals with the forces as well, okay? But the aspect of it that basically deals with forces that causes motion is dynamics. So you recall that Newton's second law of motion says that if a body accelerates, it is because of the sum of unbalanced forces acting on the body. So when the forces on the body are unbalanced, then the force is direct proportional to the acceleration that is produced. Okay? Alright, so when mathematically we say that F equal to ma at the end of the day, so m is constant for a body, except we break the mass, we destroy the mass. But given that the mass is compact, it doesn't change. What changes is acceleration with respect to the amount of force that impacts the body or the mass. So in this case, we are saying that so Newton's law is saying that it is force that causes acceleration. But in kinematics, we are not dealing with the forces at all. It is in dynamics we are going to do that. All right. Now, of course, then the third aspect is statics. So that's the third aspect of mechanics. So we have kinematics, dynamics, and statics. In statics, we basically or primarily deal with equilibrium of forces. Okay, so that's what we're going to deal with moment of force, moment of mass, moment of mass, couple, torque. All right, so that is statics. So today we are going to deal with kinematics. So kinematics, like I said, is the aspect. The word kinema is the Greek word for motion. Kinema is the word motion. So what is motion? How do you know a body is moving? Motion is movement. How do you know a body is moving? When the body has changed position with time. So you look at this body at the first second. Then in the next second, you saw it in position X. Okay? In the next second, you have seen it in position X2. Position X1, for example, if this was X0, X1. At the third or fifth second, you have seen it in position X7. It has changed from one point to another. So that body is said to be moving. Okay? The body is said to be moving. So for example, if you see the Earth, for example, we know that the Earth revolves and rotates, right? The Earth is rotating, but actually if you stand outside of the Earth, you might not really see the Earth moving around, especially because the motion is very slow. But because we are seeing time changing and the day and night, times changing in the, giving rise to day and night, we know that the Earth is actually rotating about its axis. So motion is basically what? A change in position of the body. Change in position of a body with time. So keep in mind that change happens with respect to time. Change happens with respect to what? Time. We actually say that as a change. Motion happens with respect to what? Time. Motion happens in time. So we actually say that motion is tempospatial. What does motion being tempospatial mean? Tempo has to do with time, okay? Time sequence, time signature. While spatial means space. So it means that if a body moved, the body will move in space, move within a space, right? Cover some distance and other quantities attached. But of course, we also move in time. So it is a change in space with respect to time that actually helps us to know that the body is what? Moving. I hope I've substantiated what motion is. Now that we know what motion is, let's talk about the types of motion. Now, what are the types of motion? We have various types of motion. The one that is of immense consequence to us in this kinematics is the one that is called the translational motion. Translational motion. Now, it's also called the linear motion. Now, why is it called linear? The word line. So it's motion on a straight line, okay? So when I move from here to here, I am said to have been translated. I am said to have translated myself. Why? Because I moved on a straight line. If I throw this body up, provided that this body, if this body is considered as a point mass, for example, it has only translated. We are assuming that it will only translate. Okay, but actually, naturally or realistically, the body does not just translate alone. It also involves in other types of motion. I'm going to explain that. Okay, what I mean now, let me explain that. But actually, if this body were a point mass, for example, this body will just move up and down, and that will be the motion. So that's translational motion on a straight line, up and down or sideways. Okay, now whether it's going forward or coming back, that is just translational on a straight line, motion on a straight line. So for example, a car moving on the road, that's translation. All right. The second type of motion is the oscillatory motion. Now the oscillatory motion is motion that has to do with oscillations. Okay. Now it's also called vibratory motion. So if you've seen something vibrate before, okay, vibratory motion. If you see something vibrate before, the thing is jerking back and forth. Yeah? Alright, so that's motion back and forth. So for example, you know what this is here? For those of us from my part of the world, you know what this is. So when you ring this thing, it's called a bell. You ring this thing, what happens? It goes back, this pendulum inside goes back and forth and back and forth. And if you have ever engaged in match pass before, your hand swings forth and back. That is oscillatory motion. Alright? Oscillatory motion, back and forth. We say it is to and fro movement. To and fro. Alright? Now the next thing is the next type of motion is, so example is motion of a pendulum. Motion of a pendulum. Motion of a body that's attached to a spring too. Okay? You've ever bounced and used a bouncing castle before. When you bounce yourself, you keep going up and down and up and down and up and down. But because of friction, air resistance or gravity, other things, that's why you stop bouncing after a while. But you actually, in an ideal condition, you should keep bouncing up and down repeatedly forever. All right. But the case is that your body is undergoing oscillatory motion, as well as the diaphragm of the bouncing castle as well. So that's oscillatory motion, vibratory motion, forth and back, to and fro, to somewhere from somewhere. Make sense? All right. Then the next one is I like to talk about the relative motion. Now you see, a motion is said to be relative if I compare, I'm going to talk about this in this video too, if I compare two bodies, okay? So in this case, you have to understand what is called frame of reference. Frame of reference. Now, have you noticed that if you are moving in a car and there's another car that's trying to overtake your car, Okay, now that your car is moving and another car is trying to overtake it, if you look at the speed of that car, it's not so fast. It's faster when you are standing still and the body and the car simply overtakes you, just moves past you. You see that the car zooms off, right? So that motion is faster relative to you. But if you're in a moving car already, that car that is still moving faster than your car will not be as fast as you would see it if you were stationary. You would agree with me, yeah? So that is relative motion. Motion of a body compared to another body, to the condition of another body. All right. So frame of reference means your point of view is now different, because initially at a point you were standing, and initially then in another condition you were in a moving car, which means you were also being translated, but that one was translating faster than you were. So because of that, you are seeing the body in a different speed, at a different speed, and all of that. That's the basic thing we look at in relative motion, this velocity of the cars, of the bodies. Now, the other type of motion I like to talk about is let's talk about the random motion. I've started the R's. The random motion. Now, what's a random motion? Is haphazard motion. Haphazard. Haphazard. I hope I spelled it well. Haphazard means it is going randomly, zigzag, in a zigzag manner. If I've ever attempted to catch a butterfly before, you know it was easy, right? You know, you just stretched on and it just came to it, right? No, it wasn't easy, yes, because the butterfly flies haphazardly. You know, there was one, I wanted to catch it one day. You know, it needed to dribble me, almost turned me upside down, you know, that's haphazard movement, because the guy just flies anyhow. Do you understand? I mean, of course, unless you're like me that can just control it and say, hey, butterfly, come here. Unless you're like that, you cannot really easily catch a butterfly. So motion of a butterfly is random. So there's also what is called Brownian motion. Brownian motion, motion of gases, that is also what? Random. They hit each other, collide with the container. Everybody's just moving up and down, and they're just like this. If you look at the gases, yes, that's how they close their eyes. They'll keep moving. Leave me alone. Yes, that's the way they do. So that's random motion. The motion is unidirectional, undefined. Okay, it has no direction. The next one is, I like to talk about the rolling. Okay, rolling. Let me show you something. If I've ever attempted also to roll something on an incline, so for example, or a ramp. So let's say this is the back of a lorry, a truck, for example. I put my guy here. I put a plank. If I want to roll, if I want to put a jar, a very heavy jar on this thing, into this lorry, okay? What we will do is create a ramp, put a ramp on the floor, okay, such that when we will now put the drum on it, we'll put the drum. So it's going to look something like this. Now let's bring it out here. It's going to look something like this. So what will now happen? We'll now roll this guy up. Boom, boom. So two persons will now be pushing from here. You understand? They'll be pushing and be pushing up and be pushing up and be pushing up. You know. Okay? So as they're pushing, this body will be rolling. It will be rolling. So that's another type of motion. Rolling. Alright. Another type of motion that we should also consider is the rotational motion. See, I've been considering R's. Rotational motion. Now you see, rotational motion is often confused with circular motion. Albeit they are not the same, circular motion. They are not the same, but mathematically they are the same. Okay? They are not the same because this is circular motion. When the earth revolves around the sun like this, goes around the sun, okay? But as it is going around the sun, it's not just going like me. You see, my front is still my front here, all through my journey, right? That's circular motion. So that's revolution around the sun, around the sun of the earth, revolution of the earth around the sun. But it doesn't just revolve around the sun. It also rotates about its axis. Okay, so look at my axis here. So I'm going like this, like this, like this. So you go like this. So this is I am rotating and revolving. Okay, so that is revolution. Rotation is motion about a fixed point. That's rotation. One point will be fixed. So this hand is fixed, then the other will go round. Okay. So this hand is fixed, for example, and my marker is going around that fixed point, okay? So that's circular motion, that's rotational motion. The circular motion is the body itself go round. If you have seen my video on circular motion, I showed you something, when you saw something around. The body that you attach a rope to this thing now, and the thing is moving around. This body itself is moving in circular path, so that's circular motion. But fixed to the axis, it is rotating. Is it clear? All right. So it is rotating about the fixed point. So that's rotation, but mathematically they are the same, okay? In fact, mathematically, circular body moving in circular path and a body that is engaging in oscillatory motion, they are the same. If you don't understand it, go and see my video on circular motion and also see video on simple harmonic motion. All right? So that's that. So these are the types of motion that we are going to be looking at. But basically, we are starting with the translational or linear motion. Now let's start. So before we start, we would like to look at some terminologies that we use in describing these motions, because it's those terminologies that, you know, that is the embodiment of kinematics, just those terminologies. So what are the terms that we're talking about? Now, you must first understand what is called distance that a body travels. I mean, we said that if a body moves, then it means it has been translated, it has changed position rather. So if it has changed position, it means it has covered the distance, it has moved from one point to another. That point to another, if you draw a straight line to join them, that is some distance moved. Is that okay? So that is distance. Distance is the difference between 2 points. Okay, the linear difference between 2 points. That is the distance. And it is measured in meters. So when you see meters, in any of these things we're talking about, it is distance or the second point, which is displacement. Now here is it. Listen carefully here. Listen carefully. Distance and displacement are not the same, but they have the same unit. Distance is scalar. So this guy is scalar, while this guy is vector. Now, why is displacement vector? Displacement is the shortest distance from the starting point. Distance is the distance from the starting point. Distance is simply the distance is simply how far you are from the starting point. But displacement is the shortest how far, the shortest distance from the starting point. Let me explain. Watch this. If a particular boy displaces himself from here to this place, then comes here, let's say he displaces himself by 5 meters, move 5 meters, then comes here, move another 7 meters, then comes here, move another 3 meters, then comes here, move another 2 meters, then comes here, move another, say, 3 meters, blah, blah, blah. If you say, how long has this boy moved? If you ask, how long has this boy moved? What is his distance? His distance covered is going to be 5 meters plus 7 meters plus 3 meters plus another 2 meters plus 3 meters. So altogether he has covered 10, 5, 20. So he has covered 20 meters altogether. That's his distance. But if you ask what is his displacement, that is different. His displacement is, where did he start from? He started from here. He has only displaced himself from here. Where did he stop? He stopped here. He has only displaced himself from here to here. So displacement is this shortest distance here. So which could be less than maybe 2, approximately 2 meters. So his displacement may be just 2 meters. But his total distance is what? 20 meters. Of course, it is directional. So we say 2 meters due what direction is down? South. Due south. 2 meters due south. That's his displacement. But what confuses students is that because when we say displacement, the body is displaced, blah, blah, blah. Because you did not see the south, you now think, anybody not put the direction. They don't have to put the direction. The direction is implied. That's the thing. Once you hear displacement, the direction is implied. But distance is basically the numerical value of how long distance he has covered. All right, how far he has traveled. So that's the difference between displacement and distance. But if you don't see the direction, and they tell you is displacement, the direction is implied. It means we know the direction in a way, but we are not just including it, okay? So, but there are some questions that, of course, includes the direction. All right. Now, it is also measured in meters. So when you see meters, it might also refer to displacement. Is that clear? But usually, mathematically, we just take the distance and displacement to be the same in numerical value. They are not even the same in numerical value, because I'm going to solve some questions for you. But I'm telling you that I could interchange the equations. So for example, I could tell you that velocity is displacement over time, and I say ds over t. So the notation might be the same. So for example, okay, notation, yes, that's what I wanted to say. So distance is denoted by s, displacement can also be denoted by s, or sometimes you also use x for displacement. But it's basically the same thing in notation. Is that clear? Notation. All right. Now let's go to the next term. The next term that you should know is from that distance, that's speed. So remember, we said when you travel in motion is with respect to time, right? Motion is influenced by time. So what is speed? Speed is how fast you are going in time per unit of time. Speed is what? The distance traveled over time taken. Distance traveled per unit of time. So that's why we say it is S over T. Is that clear? So that's why it is measured in, what's the unit of measurement of distance? That is meter. What's the unit of measurement of time? Seconds. So we call it meter per seconds. This is the unit of measurement, or we write it as M per S, like this. Exactly. So that's the unit of speed. But take note, there's something called velocity. Velocity and speed, they almost mean the same thing, because it also means how fast you are traveling. Speed is how fast you are traveling. Velocity is how fast you are traveling. But with velocity, we say it is how far you are being displaced. So it's displacement over time. So what does that tell you? Velocity is also what? Directional. It is also a vector, while this guy is a scalar. Scalar, vector. Is that clear now? Because speed is how fast you are going in a space, how fast you are going in any direction, that's speed. But velocity is how fast you are going in a given direction. Is that clear? In a given specified, defined direction, that is velocity. But usually the notation is also the same, so this is also x over t, which means we could also have meter per second. So the unit is also meter per second. That's the point. Is that clear? So by calculus, we tend to want to bring in what is called instantaneous speed, instantaneous velocity, but I just want to show you the notation that it's the same. That we could also say it is the change in distance, because with respect to what we are our frame of reference, we could say that where are you traveling from? Okay, you have before you started, where you started from may be your 0 point, but if we don't take it as 0 point, you have changed distance, because you probably traveled a distance to that point before going another distance. Do you understand now? So that point where you start from might not be your 0 point. So in which case we say that speed is also change in distance over change in time, or change in displacement over change in time. Is that clear? So it's the same. It's primarily the same. So we write this as ds dt or dx dt. Either way you put it. Okay? So we'll get there when we want to consider instantaneous guys. Now, let's now talk about the next step, which is acceleration. Now, what is acceleration? Acceleration is basically your change in speed over time. How fast the body is changing in speed. Now, a body might be moving steadily like this. For example, if you're in daddy's car and daddy begins to move, after a while, you just go. You see, that change, that my intonation moved up, right? So the intonation went up. So that shows you that the body that's what shows you that the body is accelerating. So that change in the sound is that acceleration, that the body is accelerating. So it means the body is changing speed per time. So the body is moving very speedily. Just like that, the body is graduating in speed. Now, another term that people tend to misunderstand with that is deceleration or retardation. Now, retardation and acceleration are the same, only that they refer to how fast you are changing speed, but they are not exactly the same. Retardation is when you are changing speed in the negative direction. So if you are changing speed in the negative direction, it means you are slowing down. Is that clear? So that is why retardation is negative acceleration. In acceleration, we use the word acceleration if the body is changing speed, but such that it is moving faster from a lower speed to a higher speed. But retardation is when the body is going from a high speed to a low speed, albeit it's still changing speed. So the point is that here we are changing speed, or now we usually use velocity. So changing velocity, we are with respect to time. So change velocity over changing time. Is that clear? Or basically just say velocity over time. That is what? Acceleration. The velocity per time. Now, number 6 is now uniform or steady. Uniform or steady speed. When you say the body is traveling with uniform or steady speed, it means that the body is covering equal distance at equal time interval. So when the body was at a particular point, it covered 2 meters after it covered 2 meters every second. When the body got to another point, again, covered another 2 meters per second. It means that that body moved with a uniform speed. Now when we get to our graph, I'll show you that when you see, when it is velocity time graph, we'll talk about graphs soon. I just want you to see this. That this point here is the point of acceleration because the body, the velocity is changing. If you look at the velocity is changing throughout. Velocity is going from here to here to here to here to here to here. If it stopped accelerating here and it began to move with uniform or steady velocity or steady speed, but now I'm using velocity, so the body will go like this on a straight line. This straight line shows that the velocity did not change. It's still at this point over this time, over this much long. This time is changing, it's changing, but it's maintaining that same speed. That's the time over which you notice that this car did not change the intonation, the sound. It kept going. Alright, so that is uniform or steady speed. Alright. I mean, of course, if the body stopped here, it will now change speed and decelerate again. So this is where we call deceleration or retardation. Is that clear? Now this acceleration is denoted by A. Okay, I didn't show you the unit. It's denoted by small a, and retardation is negative A. Now, velocity is in meters per second. So per another second, that will be meters per second squared, or ms raised to the power minus 2. Is it clear? That's the unit. Then uniform or steady speed is when the body is covering equal distance in equal time interval. Is that clear? So now the next one is uniform velocity. So what would that be? Equal or steady velocity, that is what? Equal displacement over equal time interval. At equal time interval. Then number 8 is uniform acceleration. So it means that the body is accelerating uniformly. It means that the acceleration is not jerking. It means it's changing speed, equal speed over a given time period. The speed change is the same over a given time. Is that clear? That is uniform. That's what you could just call uniform or steady. Is that clear? Now let's now go to instantaneous. So let's start with instantaneous. Instantaneous. I like to take velocity instead of speed. Instantaneous velocity. So you notice that the same apply for speed, okay? But it's just that is non-directional with speed. Now what is instantaneous velocity? The body is set to engage in instantaneous velocity if the velocity changed at different times, non-uniformly. So if the velocity changed at different times, we want to get the velocity at a particular time. We don't speak a particular time. So to take that velocity at a given instance, we call it instantaneous velocity. So that is velocity at a given time, at a specific instance. So to take it, instantaneous velocity is given by dx dt. That is change in x over change in time. If you know a little bit about calculus, you will know that when we want to change when we want to take, for example, a y function that looks like a curve like this, the velocity, for example, if it were a linear function, the y function will change at a steady rate rather, with x function, with x variable. So the y will change with respect to x at a steady, but if it becomes a curve, it's no longer steady. At every point here, we cannot get the same answer for the change in velocity. So since the velocity is changing at different times, to now get the distance, the distance is changing at different times. So because distance is changing differently, it's not steady. To now get that, to get the instantaneous velocity at a particular time, we'll now take the tangent, the change. We call it the slope of tangent. Is that okay? Well, when I release my video on calculus, I will release some videos, okay? Maybe I'll link them in the description. We call it gradient of a tangent. So if this curve represents the curve around which the guy moved, I told you the body can just displace itself anyhow, can travel distance in different ways. But at the curve, the gradient of the curve, I'm bringing in terms now that you might not understand. But just remember that instantaneous velocity is change in speed by change in time, dx dt. So so we are starting from here. If, for example, we are starting from here, let's start from here. Let me quickly explain this. So just recall that instantaneous velocity is dx dt. I'll show you how to treat that. So watch me now. We'll start calculation soon. Now there's also the last one that is called instantaneous acceleration. Now what is instantaneous acceleration? Instantaneous acceleration is just acceleration at a given time interval. So here we said the body is not traveling at regular distance. The distance is not regular. So because of that, we have to take the velocity at a given instant. The same way, the velocity is not in this place. Acceleration is velocity over time. So the velocity is not regular again. It's not steady. It's not uniform. Okay? So because of that, we have to take the velocity at a given instance in time. So we take it as what? dv dt. That is change in velocity over change in time. All right. Now let's get to some calculations. So these are the terms you have to understand. Before we start derivations at all, you see, we have started to solve questions. So in order to be able to solve a question like this, for example, the question says, calculate the distance moved, or the total displacement. Let me use vector. The total displacement of a body whose motion is according to the expression, is according to the displacement function. So the displacement function x in terms of t is equal to 2t cubed plus 60t minus 60, let me use small numbers, minus 5, for example. In order to be able to solve this question, at t equal to 5 seconds. So at 5 seconds, what's the total displacement of this body? That's what this question is asking. Now to be able to solve this question, it's very easy. What you do is this. It says you find the displacement at that time. Simply plug in the value of t into this equation, because this is the equation that defines the displacement with respect to time. This equation defines the displacement with respect to what? Time. So what do? You simply plug in the value of t into this expression. That's t, record that x is displacement. That's 2 into bracket 5 raised to power 3 plus 6 into bracket 5 minus 5. This becomes 2 into bracket 5 raised to power 3. That is 5 times 5, 25 times 5, 125. 125 plus 30 minus 5. This is 25. 2 times this, 250 minus 25. That becomes 225. So the answer is 225 meters for this body, 225 meters. Now, but what if the body now says, calculate the instantaneous velocity, the velocity of the body. Now, this is where your knowledge of calculus comes in. So you need to understand calculus. Let me quickly teach you basic calculus, the most basic part of calculus. If I have a function like this, that y in terms of x is given by, this should not bemuse you. This is just saying that the y function is defined by x, okay? It is defined with respect to x, anyhow you hear of it. So if I have 2x, let's say, let me use another number, 4x squared minus 2x, for example. And I'll say find dy dx, because here we said instantaneous velocity will be what? Dx dt, right? So the same way, it means we are differentiating y with respect to x. Exactly, differentiating y with respect to x. It's very simple. This is what you do. This is what you do. It's called differentiation. Now the opposite of that is integration. I'll show you what that is. Now watch this. I will differentiate this by bringing this value here, bring it down. It's very simple. Just follow the step. You don't need to know the nitty-gritty yet. Just follow the step. Bring this guy down to multiply this. It becomes 2 times 4. Then x is here. This power, reduce the power by 1. You no longer put 2 here. 2 minus 1. Exactly. Minus, do the same for this guy. What number is here? 1. 1 times 2, 2 times x raised to power 1. This one will reduce by 1 as well. Exactly. This becomes 2 times 4. 8x raised to power 2 minus 1. 1 minus 2x. X is now raised to power 0. Anything raised to power 0 is what? 1. So 2 times 1 is 1. So this is our answer. Exactly. So next time you don't even need to touch your paper. Just do this. Let me show you another example first. If I say y, if you already understand this, just skip the video. Skip the video. This is for those that don't understand it at all. Just watch what I'll do. If I say y in terms of x is given by 4x raised to power 3 minus 2x squared, or 3x, let me use another number, 5x squared, because I'm liking 2 and 4 and, you know. So dy dx is equal to, this guy comes down here, that will be 12, right? Multiply this guy, 12. X raised to power, reduce this one by 1, 2. Makes sense? Then minus, this guy comes down, 10. X raised to power, reduced by 1, 1. So this is our answer. Is it clear? Good. So we are going to do the same thing here to this expression. But let me quickly show you what is called integration. Because to go from velocity back to distance, we integrate. To go from distance, distance to velocity, we differentiate. And to go from velocity to acceleration, we differentiate again. Is it clear now? If I want to differentiate this thing again, we write it this way: d squared y dx squared. Now here is it. This is the reason why we are not writing dy squared, because y is not a term, y is a function. So we differentiate, we put the square on this guy and not on the function, then dx squared. X is a variable. It could be a term, okay? So equal to, so d squared y dx squared is equal to differentiate this the same way, bring this 1, this power down. Remember we have differentiated it first, we got this. Bring this power 1 down, we still 8. X raised to power 1 reduced by 1. X raised to power 0. That is 1. Anything raised to power 0 is 1. 1 times 8, 8. 8 becomes our answer. Exactly. Because then you say, what of this guy? X is already raised to power 0 here. 0 times 2, 0. So when you differentiate a constant, in maths, this is called a constant term. You get 0. When you differentiate a linear expression, you get constant. Exactly. Let's try to do d squared y dx squared here. This is the differentiation. I'll show you integration now. I'll show you integration. In integration, I'll show you why the whole thing is sweet. Look, this is d squared y dx squared. Let's differentiate this. This guy comes down, gives us 24x, reduced by 1, that's 1, minus 1 times this 10, x raised to the power 1 minus 1, 0. So this one disappears. This is the answer. Is it clear? Then you ask, can we go further? Yes, you can go further for maths. But in physics, we don't need to go further because it's just 2 stages. So I'll show you. Now, then you now ask that, Master, what do you want to go from here to here? Now, actually, mathematics is harder to go from here to here for this expression. But it's easy. I can go from here to here. It's easy. So let me go from here to here. Let me go from here to here first. This one is easy. I'll show you why I say it's hard to go from here to get exactly this. I'll show you. But let us go from here to here. That process is called, this one is called differentiation. So I just differentiated. But the next stage, the process that reverses it is called integration. Now, integration is just the opposite of differentiation. We call it anti-differentiation or anti-derivative. Now, anti-differentiation means this. We will reverse the process. What was the first thing we did when we wanted to differentiate here? We brought this power to multiply this guy down, right? That was the first thing we'll do. What's the opposite of that first? Let me ask you. What's the opposite of bringing this guy to multiply this? It will be what? Bring this guy to divide, right? Let me repeat that. The opposite of bringing this guy down to multiply, which was the first thing we'll do, is the opposite of that is bringing the same guy to divide. But that will be the second thing we'll do in this place. So the first thing we'll do in this place is the second thing we did here. What was the second thing we did here? We subtracted the power. We subtracted 1. We reduced the power by 1. We subtracted 1 from the power, right? So what's the opposite of subtracting 1? Is adding 1, right? So that's the first thing we'll do here. It was the second thing we did here. So if I want to integrate this, so now I have that d squared y dx squared is 224x minus 10. Integration, we'll put this sign, okay? We'll put this sign. So d squared y, integral of this, 24. Let me not bring in all the notation. Let me just show you how to integrate it. Let me just show you how to integrate it. So what did I say we'll do first here? Is the second thing we did here. The second thing was to reduce power. Here we'll add power first. So this becomes 24, x is to power, add power. X was this power 1 here. Add 1 to that, right? Then divide, because the first thing we did here was to bring this power to times. So before reducing it, now we have increased it, then we now bring it to divide. Is it clear now? The opposite. Alright? Then plus 10 here. X here is just about 0. Let's increase that 0 by 1. Let's go at 0 plus 1 over 0 plus 1. Is it clear? So this becomes 24 x raised to power, this x raised to power 2 over 1 plus 1, 2. Here 1, here 12. Plus 10 x raised to power 1. 0 plus 1 is 1, so we'll leave it like that. So this becomes 12x squared plus 10x. 12x squared plus 10x. Sorry, minus. Sorry, minus. I'm sorry. Is it clear now? Alright. So that's just that. Here, if I integrate, I might not get this 2. We usually add what is called the constant of integration. But let's not get into that. But I just proven to you that we can go up and come down, like that. So let's use the knowledge that we just garnered from here. Let's use it now. Alright, so how do we solve this question? The question has said, calculate the velocity at t equals 5 seconds. So first, what is velocity? Velocity is dx dt. And what is our x in terms of t? That is, we are differentiating 2t cubed plus 6t minus 5 dt. So let's differentiate this. V will become, differentiate this. This will come down to multiply this. 6t squared plus differentiate this 6. Makes sense because 1 will come down to multiply 6 and we'll reduce by 1. So this is what we have. So this is the velocity, this is the expression for the velocity in terms of time t. So v in terms of time t at 5 seconds, at t equals 5 seconds now, will be equal to 6 into bracket 5 squared plus 6. This becomes 6 into bracket 5 squared is what? 25 plus 6. 3 times 2 times this, 2 times this, 50. 50 times 3, 150. 150 plus 6, that is 156 meters per second. So that is the velocity. Is that clear? Now, what if we ask to find the acceleration of this body? So what is acceleration? Acceleration is now dv dt. That is, we differentiate the expression for velocity again. So what's the expression for velocity? That is that. It means we differentiate 60 squared plus 6 dt in terms of time, or with respect to time. So the derivative of this gives us what? A equals 2 will come down to multiply this, that's 12. 12t. This one changes to 0. So our answer is 12t. So at time equals 5 seconds, the acceleration will be equal to 12 into bracket 5, that's what? 60 meters per second squared. So that is the acceleration. Did you say I just solved that question? Good. That is very good of you. Now, quickly, let's get into what is called graphs. Graphs. You see, these graphs that sometimes confuse students. Now, I will give you graphs and quickly show you how we graph them, okay? And solve questions. We'll solve just one question. I will be off. Now, if you need more questions for practice, reach out to me on my WhatsApp number. My WhatsApp number is 090-2141-6307. And shout out to some of my students who reached out to me for this. Mr. Umar Bashir. So, and that's one of the reasons I'm shooting this video right now. So now, what was that? Graph. Let's talk about graphs. Now, there's something called there are different types of graph. We have the displacement time graph. What does this mean? It means we are graphing the displacement of the body, the displacement x of the body with respect to time, against time rather. All right? So if it gives us a steady graph like this, we also have distance time graph. It means that we are just looking at distance with respect to time. So but I like to talk about displacement. So displacement time graph, that is that. So now, you see that this graph is sloping. What does this tell you? This tells you that the body is changing distance or changing displacement as time is also increasing. Displacement is increasing as time is increasing, isn't it? So to look at that, to look at how much one, for example, displacement is increasing with respect to time. That's what we call the slope. We take the slope. Okay? We take the slope. Now I'm going to tell you about position now so you understand where this graph is coming from. We take the slope. So how do we take the slope? Now, we take the slope by, you remember slope, if you know slope, maybe I'll talk about position now. Let me quickly talk about position before, so that you understand this. But let me quickly show you what slope is. The slope of a velocity time graph, of a distance time graph, of displacement time graph is velocity. While the slope of distance time graph is speed. And that makes sense. Slope means change in one variable y over change in variable x. What did we graph here? X, distance. So change in x over change in variable x. What is x? What did we graph in x-axis? Time. Change in t. What does that show you? Velocity. Is that clear now? So that's why the slope, that is how slopey it is. Alright? That is what we call the velocity for displacement time graph. Now, what if we now have a velocity time graph? This should already tell you what we are getting at. If I graph velocity against time, now what will happen? If I have a slopey graph here, No, what if I have a graph that is not sloping here? What if I have displacement against time and I have a graph that is like this here? No. This graph shows you that as displacement is increasing, as time is increasing, displacement is increasing. It means it's traveling more distance or more displacement per time. That's the meaning of this graph. If the graph were to look like this means that the distance is reducing with time. Now you might not say, how is this one possible? Now this is only possible if you take, let's say someone is returning somewhere. So let's say the body has traveled somewhere before, then it's now returning back to the starting point. That's when you take a graph like this. Exactly. But naturally the displacement always increases, okay? Because the distance the body is traveling is increasing. Okay? So that's my point. But what if we graphed it and it turns out to look like this? Now this is showing you that as time is increasing, the body is not changing any displacement. It's not displacing itself. Then you now say, now watch, this is different from distance. So this, when you have a graph like this, for distance time graph, this one means that the body is not moving at all. This. While this one means the body is not displacing itself, like this. What? They are different. This one is displacement time. This one is distance time graph. This one says, this is an example of what is happening here. This one is just, the body is just at a point. Point A, it doesn't move from point A. But this one is when the body moves. For this one, the body can still move. This one, for example, is when the body moves from, like, for example, move from point A to point B, then goes to point C, then goes to point D, then comes back to point A. This body has zero displacement. Is that clear? Because it returns to the starting point. But if you want to graph distance here, it will not look straight because the body has changed distance. Even though it returns to the starting point, the distance it has moved is going to be the distance from here to here plus distance from here to here to here to here. Is that clear? To understand further, watch my video on vectors. Is that clear? So you see that there are different graphs. All right. Now let's talk about velocity time graph. It's not velocity graph, velocity time. This is just saying we are graphing velocity against time. Now looking at this, if I have a graph that is sloping like this upward, it means it's a positive slope to show that the velocity is increasing as time is increasing. So the body is increasing speed as time is increasing. So the slope tells you that it's what? The change in velocity with the change in time. So this is going to be what the acceleration of the body. How fast the velocity is increasing with respect to the time. And since the body, since it's a straight line like this, then it's called uniform velocity. Uniform velocity. Uniform velocity is not constant velocity. Let me show you constant velocity. What if I plot a graph of velocity against time again now? And I have a straight line like this. This tells you that the body is steady. The body, that the velocity is constant. It's not changing. Look at it. It's remaining here even as time is just going forward. But look at this one. As time is going forward, at a particular point here, velocity has changed from this point. Velocity was here. If you check this point here, velocity is now here, time is now here. So this is steady, uniform, but it changed. Here, velocity is constant here. But what if I now plot another graph and I have velocity against time such that I have a downward slope? This is telling you that the velocity at initial point, the velocity was high. Makes sense? It means the body has already been moving since, okay? And at this point here, the velocity was here. But at this point, the velocity now reduced downward here. At this point, the velocity reduced downward here again, keeps reducing until it probably go to zero, but we don't know if it got to zero. But you notice that the time from here, it increased to this place. Time is increasing this direction, velocity is increasing in upward direction, but this our own velocity is coming down. So it means that the speed is reducing. So it means the body is going to a halt. So we say the body is retarding. So this is what we call deceleration. You notice, slope, acceleration, deceleration. So the slope of velocity time graph, slope of VT graph is what? Slope of VT graph is what? Acceleration or retardation. Acceleration or what? Retardation. All right. I guess I'm tired. Let me take water. All right. So, alright, I stopped at showing you deceleration of velocity time graph. Alright. So, but there are some other types of velocity time graph that you might encounter. For example, the velocity time graph for an object that is thrown upwards, for example, is this. It's such that when you throw the object upwards, you see that over time, you see that the body after a while will stop going up, stop flying, to begin to come down, right? If you stopped flying, if you couldn't go further, it means it attained zero velocity. Do you agree with me? The body attained zero velocity, it means it stopped. For it to stop, it means the velocity became zero somewhere, right? And for velocity to become zero at a point, the body cannot just go from 5 meters per second to zero. It dropped up till that zero. It means that when you throw an object up, the object velocity will be reducing per time as it goes up until it gets to a point where it can no longer go up, where the velocity is zero. Is that clear? So if that's the case, then it means that the point of your projection, the point of throwing from your hand, is the point where it will have its maximum velocity, and that velocity will reduce as it gets to zero at the maximum height before it increases again if you throw it upward again, then come down like that. So that's why the way we graph the velocity time graph for an object, this one is object thrown upward. Okay, but what if we drop the object by itself? Is bouncing, going up and down, going up and down. This way we graph it, velocity time graph. It looks somewhat like this. It goes up, comes down, goes up, comes down, goes up, comes down. Is that clear? So this is the velocity time graph for a body that is bouncing upward and downward. Bouncing for a bouncing body up and down. Is that okay? So that is it on velocity time graph. Now let's solve a question on velocity time graph. Let me quickly take my time to write one question. And I promise you with that one question, you should be able to graph any expression. Then we'll move further. Is that okay? We are moving speedily. But also make sure that you are paying attention to every detail so that you will understand everything. I promise you are going to get it. Amen. Pause. All right, so let's solve this question on the board. Now, I want you to, because this is the only question I'll solve on this, I want you to look at the way I'm going to interpret these questions. It says, a train starts from rest. Now, when you hear that word from rest in your question, know that the body is starting from the origin. The body is starting from what? The origin, zero. So if I plot my graph like this, it means I'll start from origin zero here. I put the velocity here, time here. So I'm going to start from here, from origin. Is that clear? Now, you know there are two types of velocity. We have the initial velocity of the body and the final velocity of the body. So the final velocity of the body is what we actually denote by V, while the initial velocity of the body is what is denoted by U. So in this case, when you hear any question where you hear that initial velocity any question where you hear that the body is starting from rest, that your initial velocity of the body is zero. That is, the body was not moving at all before, so U is zero. So let's go on. And accelerates uniformly until it reaches a velocity of 40 meters per second after 10 seconds. So in time, it moved for 10 seconds. So it accelerates uniformly. So you use a straight line because the acceleration is uniform. Use a straight line, this acceleration phase, and the acceleration is not given, we don't need the value. But it got to this velocity of 40 meters per second. Velocity is measured in meters per second. So that's how the acceleration happened. So it happened for 10 seconds. So we record 10 seconds here. Time is measured in seconds. Is this clear to you now? So I use a straight line to show you that now it must be a slope, not a straight upward line, because a slope shows that it is accelerating. The slope of VT graph, remember, is acceleration. Okay. Now, until it reaches a velocity of 40 meters per second after 10 seconds in time. It travels with uniform velocity for 20 seconds. So it travels with constant velocity, that's what it's saying here, not uniform. Constant velocity, that is this same velocity. It did not change for another what? 20 seconds. So double this time. So from here to here, double it to around this place. So if you travel that for 20 seconds, so this space is 20 seconds. What will be the next time here? 20 plus this 10, that's what? 30. So we know that from here to here is 20 seconds. So this velocity did not change, it's still 40 meters per second. And then comes to rest in 15 seconds. So in the next 15 seconds, what it did was to rest. So let's draw another line here to show us that it rested after 15 seconds. 15 seconds plus this 30 seconds it has moved is what? 45 seconds. Is it clear now? So this is the graph, and this is the most basic type of question for velocity time graph. So this is the graph of the velocity time graph. If the body says after moving here, now accelerate again, you plot, you draw it up again, makes sense, and continue like that, depending on the shape. Then you now ask, what is the use of this thing? This is the use. It was discovered that the area under this whole curve, the area of this whole shape, is equal to the total distance traveled. Yes, that is one use of velocity time graph. The area under a VT graph, the area under a velocity time graph is distance traveled, is total displacement or total distance. It's actually total distance, not just displacement. Well, for velocity displacement, okay. So if you see displacement or distance, that's what you see, either of both. Choose one. It's total distance. The area of this shape plus the area of this shape altogether gives the total distance. So that already suggests to you that this last question that says you calculate total distance traveled is just area we'll take. Is it clear? Now let me show you some formulas that you need to know for now, okay? We'll derive those formulas soon. That is the next thing we're going to do after now. We'll derive formulas. Or we'll take relative velocity first, then we'll derive formula. No, let's derive formula first, then we'll take relative velocity. Now watch, see. This formula, V equal to U plus AT. I want to teach how to use the formula directly. How to use the formula directly. Now, or if you don't want to use formula, recall that acceleration, what's formula for acceleration? Change in speed, change in velocity over change in time. And what is change in velocity? New velocity minus former velocity over time. Is that clear? So the question says that we should calculate the acceleration of the train. Very easy. Acceleration of the train, I. Acceleration of the train will be equal to, the new velocity is 40 meters per second minus former velocity. What's former velocity? It started from rest, so former velocity is 0. 0 over, what is the change in time? It went from 0 seconds to 10 seconds. So 10 seconds minus, that's new time minus old time, 0, equal to 40 over 10. Over 10, sorry. So what does that give us? 4 meters per second squared. So that is the acceleration of the body. Is it clear? Then the next question says we should calculate the retardation of the train. Retardation. Let's go again. What is retardation here? Retardation still is what? Change in velocity over time, right? So negative acceleration is equal to what? Change in velocity over time, over change in time. Now what is the change in velocity? Where is the retardation phase? Where did the body retard? This is where the body retarded. So this is where the body retarded, over. So this is where it retarded. That will be the change in velocity, that will be final velocity. What's the final velocity here? It came to 0, right? So the final velocity is 0 minus, what's the former velocity? 40 over, what's the time taken to retard? From here to here is 15 seconds, right? So put 15 here. So this becomes minus 40 over 15. 5 here 3, 5 here 8. So that becomes 8 over 3, which is 2 whole number, 2 over 3, that's 2.67 seconds. Negative that, negative cancel negative, so A equals to 2.67 seconds. Is that meters per second squared, sorry, meters per second squared. So that is the retardation. Now let's go to the third question. The third question says we should calculate the distance traveled after 10 seconds. After that 10 seconds, what's the distance traveled? Remember I told you that the area under a velocity time graph is what? Is distance traveled. It's total distance for this entire curve. But for this, any part of the curve is distance. So if I want to take the distance traveled after 10 seconds, it's just the area of this curve. What's the 10 seconds? This is 10 seconds mark. So the area of this curve, what curve do we have here? A triangle. Make sense? The area of the shape we have there is a triangle. The shape we have there is a triangle. From 0 to 10 is 10. This place is 10. Height of the triangle from here to here, 0 to 10 to 40. That's 40. So recall that the formula is formula of area of triangle. Because we said the area, the distance is going to be area of that shape. So area of triangle. You can name it triangle ABC, anyone. So area of triangle is half base times height. What's the base here? Base is 10. Half times 10 times what's the height here? 40. So here 1, here 20. 2 times this, 200. So the answer is 200 meters. That's the answer there. 200 meters. Now the next one says, that's question V now. I hope it's still visible. Question V says, or IV, sorry. IV. Let me be sure that it's still recording. IV, good. Yes. IV is the distance traveled during retardation. Now what's the distance traveled during retardation? Where is retardation? Here. So what shape? The distance is still what area of that curve. What shape is this again? Another triangle. So that is half base times height. What's our base in this case? From here to here, 15. From here to here, 40 still. So that becomes 1 over 2 times base, 15. Height, 40. Here, 1, here, 20. 20 times this, 150 times 2, 300 meters. So you traveled 300 meters in the retardation phase. Then the last question now says, which is V. Question V says the total distance traveled. How do you calculate total distance traveled? Just do the area of this shape. So that will be the area of the first triangle. Area of the first triangle plus area of this shape. What's this shape? Rectangle plus the area of the last triangle. So I'm just rewriting it in case in a question where we have not solved it before. So here we have solved this before. What did we get? We got 200 plus the last guy we got 300. Okay, so this middle here is rectangle. What is the rectangle here? So let's do area of rectangle. The rectangle is this. From here to here is 40. Actually, if we drew this incorrectly, this one should be longer, okay? This should be longer, but it's not drawn to scale. So from here to here is 20. So which is mathematically not correct. It's supposed to, but let's just leave it that way. So 20 times 40. Now length times breadth, that's the area of a rectangle, right? So what's the length here? It should be 40 times breadth is 20. That is 800. So 800 plus 200 plus 300. That is 1,300 meters. And that is the total distance traveled. Say total distance traveled. Good. You see this formula that we wanted to use, we did not use it again. So let's go back. Let's now go to deriving equations. Then we'll go to relative velocity. Let me pause it again to clean the board. Pause once. Alright. So let's continue. Now let's go to derivations now. Derivations of equations. Now let's start with the basic equation. Remember I said that acceleration is equal to change in velocity over change in time, or over change over time. Now we usually say just over time. Why? Because our reference point from starting, because time never really stopped for anybody. The distance may be from your house to somewhere, but time has started before you started your calculation. So time is always marked from 0 points. The point of starting is marked as 0 to the point of ending. So the point of ending is the time difference is going to be from 0 to that point. So that's why we don't usually use change in time. Okay? So we can easily write time, but the velocity is changing. Is that clear? So if there are two velocities, I said one is v final and the other is u. Okay, so we now say change in acceleration of what? V minus u, the change over t. Exactly, the difference is the change. So by the time we do this, now this is the first equation that we need. Now from here we can derive an expression for final velocity. So for final velocity, v will be equal to what? Cross multiply. When you cross multiply, you have that v minus u equal to at, right? So from here, u will come here. So v will be equal to u plus at. This is equation. This is the first equation of motion actually. Is that clear? V equal to u plus at. Now from here, there's another equation you should learn that is also basic for by definition, just like we took this one by definition. Remember the average speed. What's average speed? Average speed is equal to what? Total distance traveled over total time taken. Total distance traveled over total time. Right? Good. Now what does average mean? Average means when you add everything together and divide it by how many things you have there. In the case of our own speed or average velocity here, and speed because we use distance. So it means average velocity will be total displacement over total time. So I'm using velocity now, velocity. Now what is average of speed or average of velocity here? There are two velocities. We have the new velocity and the initial velocity. So when you add them, you take their average by dividing their two. So divide by 2. So this average velocity should be equal to total displacement over time. Is this clear? So from here we can get an expression for S. S becomes, we cross multiply, so that's 2S equals V plus U multiplied by T, divide both sides by 2. So S becomes V plus U over 2T. Is this clear? So this will be equation 2 actually. So if we take this by definition, this will be our equation 2. Alright. Now recall that from equation 1, we just said that V is U plus AT, right? So let's use U plus AT to replace V. Replace V in equation 2. So what's equation 2? Recall that equation 2 we got to be V plus U over 2 times T. So anywhere we see V, we put U plus AT. So S equal to U plus AT plus U over 2 multiplied by T. S becomes U plus U, 2U plus AT over 2 multiplied by T. S becomes 2U, multiply everything by T, this bracket, T, this guy up here, this one is T over 1 now, so 2 times 1 is 2 over 2, T times everything here, 2UT plus AT squared. By the time you separate this, remember in math, that if I have X plus Y all over A is the same as X over A plus Y over A. How did I get that? LCM of A and A is A in A, 1 times X plus A in A, 1 times Y. You see we got it back. So when you split this, it should be this over the denominator over the denominator. It means they share the same denominator. Right, so the same way here, I'll split this guy here. I'll have that S equal to 2UT over 2 plus AT squared over 2. So 2 takes care of 2, so that S equal to UT plus 1 over 2 AT squared. I mean, we use 1 over 2 because if we multiply this by 1, it's still the same thing. So these are equation 3. Are you with me? Good. Now let me show you something. You know that from this equation, I can make T subject of formula by bringing T here. You know that AT will be equal to V minus U. V minus U. Divide both sides by A. T equal to V minus U over A, right? So since T equal to U, V minus U over A, I will still substitute that into that same equation 2. So you see equation 2 is very, very interesting. I can do another thing by substituting T here, but It might be more complex for students that don't understand. So I like to use a simpler one here. So which is S equal to V plus U over 2 multiplied by T, and this one is faster. What is our T here? Recall now that we have gotten that T is V minus U over A. So we plug into the equation, S becomes V plus U over 2 multiplied by T, which is this, V minus U over A. Now let me show you something. Okay, let's even do it that way. So S equal to V times V. Let's multiply. 2 times A, we need to give us 2A here. V times V, V squared plus V times U, that's minus UV. Minus UV, U should come before V. Then plus V will now open this bracket again. Plus U times V, UV. Plus times minus, minus U times U, U squared. So from here we have S equal to U minus UV plus UV is 0. So S equal to V squared minus U squared over 2A. You cross multiply, you can obtain an expression for V. So V squared minus U squared is equal to 2AS. From here, let's use U squared come here. V squared becomes U squared plus 2AS. This is equation 4. So these are the fundamental 4 equations of motion. Now you ask me, Master, how can we not take square root of both sides to make this subject? You are still correct. Only that we prefer this form. We prefer this form for the equation. So our 4 fundamental equations of motion are the following. V equal to U plus AT. S equal to, we call it the Suvat equation. S equal to UT plus 1 over 2AT squared. And V squared, try again. V squared equal to U squared plus 2AS. And S equal to U plus V over 2 times T. And you ask me that why did I not put it here? I like to go SV, so you remember. Alright, those are the equations. So I can clean all of this. Now what we'll do next is we'll apply, let me quickly show you what's called relative velocity. Then we'll now apply these equations to solving questions. Then from here directly we'll move to projectiles. Then from there directly, you understand, we're progressing here? Good. So let's solve some, let me quickly show you what is called relative velocity. Let me first show you this before. I have told you that, let me first show you this rather. I have told you that if you are standing on a spot and a car speeds up across you, the car will look like it's moving very speedily, right? Good. Now you will notice that the car will actually move even faster than that if you were moving in the opposite direction. Recall that, or take note of this, anytime you are moving in a vehicle and another car is moving in the opposite direction, when you guys pass each other, there is a sort of vroom that you hear, there is a kind of sound like that, right? Is that because relative to you, it's as if the body is moving faster, the velocity you see will be faster. Is that okay? But if the body were to be moving in the same direction as you, and you are also moving, you see that it will move slower in a way. Or if you are standing, the velocity will be fast, it will be fast, but it will be faster than when you are actually moving. Is that clear? Alright. In fact, if you have tried it before, run with a car, you see that even though the car is faster, at the point it will look like the car is not as fast as it actually looks. Okay, so that's what we call relative velocity. So it is such that if I ask you to find relative velocity, if the bodies are moving in the same direction, let's say body A is moving in velocity of V sub A, body B moving velocity of V sub B, the relative velocity V sub R of A and B is equal to, if they are moving in the same direction, what will happen? It will look like one is slowing down a little, right? So it will be V sub A minus V sub B. This is saying that velocity of A with respect to velocity of A from the perspective of B. Then V sub R is the same as V sub B minus velocity of A if you are looking at velocity of B from the perspective of A. Is this clear? So if I say, for example, a man was traveling northward with a velocity of 20 meters per second. Another man is traveling northward with a velocity of 5 meters per second. The first guy, 20. The second guy, 5. If they are traveling northward, what will be their relative velocity? It will be 20 minus 5, which is 15. Is it clear? Very simple. If they are traveling in opposite directions, what happens? Then a different thing happens. If you are traveling in opposite direction, that's why you see that the body, if a car is traveling opposite to you, you hear boom, as if it zooms off, right? Because it will look like it's faster. If you are traveling in opposite direction, it will now be V sub A minus V sub B, because the direction is different. So this becomes V sub R becomes V sub A plus V sub B, and that will be the answer. So you add it up. So for example, for that my example, one body is moving upward in 20 meters per second, the other body is moving downward 5 meters per second. Their relative velocity was 25 meters per second. And that's all about relative velocity. All right, now let's go on to solving questions. I'll pause and quickly write some questions down. All right, so you will notice that I have only 4 questions here. Now I use these 4 questions because these 4 questions are the only ones that are associated with a horizontal motion, and we are talking about horizontal motion so far. So these equations actually flip, they change when we get to vertical still linear motion. But quickly, let's solve this question because the power might soon go off now. Let's go. It says the body starts from rest. Remember, when you hear start from rest, I told you u should be what? 0. And accelerates uniformly at the rate of this. A is what? 3 meters per second squared for 10 seconds. Time is 10 seconds. How far from the starting point will the body be? How far from the starting point? What are we looking for? S is what? So which of these formula are we going to use? That's one question that students tend to ask. How am I going to know the formula you have to use? You can use any of the formulas if you know how to combine them. For example, when you see this, you have S, U, A, T. Is there any of the formula that combines everything together? If there is, you can go on, but there is none. Use the ones that have parameters here. Then to find something that will use another one to find another thing. I don't know if you understand. So for example, I will use 2 formulas. Let me see. This one, SUAT, SUAT. So is this formula I will use directly. I cannot use VUA2A. I can use it to get it. If I let me prove it. Let's quickly use S equal to UT plus 1 over 2AT squared. You see how I judge the formula to use now because I know the things that are given and the thing I'm looking for. So that's how to first parameterize your equation. So S is what we're looking for, equal to U, which is 0. So 0 times T. When U is 0, our equation changes. Let me quickly show you some transformations. When U is 0, our equation S becomes V over 2 times T, V equal to AT, S equal to 1 over 2 AT squared, and V squared equal to 2AS. When U is 0, when the body starts from rest. Is it clear? So 1 over 2, A is what? 3 times T, which is 10 squared. S becomes 1 over 2 times 300. 100 times 3, 300. Here 1, here 150. So the distance covered is what? 150 meters. So that's the answer for that. Now, you now, as I promised, I said I could use another formula to get it. For example, if I want to use this formula to get it, because I know that there is S here. If I want to get for S, I know there is V. I have to first calculate for V. But U is already 0, so our formula transforms to this. So we need to first calculate for V. So from here, we can first say that V is equal to U plus AT. Now what is U? U is 0, so V is now AT. Right? U is 0, so V equal to, to use this formula, we need V. That's why I'm using that, okay? So V is A, which is 3, times time, 10, that's 30. V equals to 30. Then we'll now go to that equation. Equation now says V squared equal to 2AS. That is 30 squared is equal to 2 times A. What is A? 3 times S. Divide by 3 times 2, 6 over 6, here 1, here 1. 30 squared, 900 over 6 is equal to S. S equal to, here, 90, 15, 150. So the answer is 150 meters. So you see it's the same answer regardless of the formula you use. Just know how to combine them. Don't begin to scramble about which formula to use. Just first go by what you have been given. Is that okay? All right. I'm trying to rush up because of the time. I'm attempting to still treat projectiles here, projectiles. So let's be quick. Now, the question 5, you see I wrote only 4 questions. The question 5 there has to do with vertical motion. Let's quickly do number 2. It says a body moves from a velocity of this, so initial velocity is 5 meters per second, and accelerates further for 6 seconds. Accelerates further for 6 seconds. Time is 6 seconds, please. So what is the acceleration? Is A we are looking for. If you cover a distance of 20 meters, if distance S is 20 meters, so what do? We're looking for A. So we say that, recall, we still have SUAT here. So you can still use the same formula, that S equal to UT plus 1 over 2AT squared. Thank God we even have U now. So S is 20 equal to U, which is 5 times T, 6 plus 1 over 2A, which is what we're looking for, times T, which is 6 squared. So 20 equal to 30 plus 1 over 2 times A times 36. Here 1, here 18. So 20 equal to 30 plus 18A. 30 should come here. It will become 20 minus 30 equal to 18A. We have minus 20 minus 10. Minus 10 equal to 18A. Divide both sides by 18. Then A will be equal to what? 2 here 5, 2 here 9. So that becomes 0.55 something. So 0.55. Approximately 0.56 or so. 556 meters per second squared. That's the acceleration. Is this clear? Okay, but then you now tell me, Master, there's minus here. Yes, you are correct. This one only tells us that the body is retarding. The body is retarding. What's the acceleration covering if it covers this distance? So the body is retarding. We will get that minus. Is that clear? All right. Now let's go. A vehicle travels at that V or U. Okay, travels at this. We don't know if it's U or V we should use for this first. Is brought to rest in 5 seconds. Brought to rest means the final velocity it attained was 0. That's coming to rest. It means that this one was former then, that U is 25 meters per second. Exactly. A body that was traveling at this was brought to rest. V is 0, U is that 25 meters per second. Find the distance covered before stopping. Find S covered before stopping. Very simple. Which formula do you use? Now in 5 seconds, time is given. So just SUVT. Which formula? SUVT. So this is what you should use. You can use any other one, okay? Like I've proven before. But you should know how to combine them and know how to use them. S equal to V plus U, that's 0 plus 25 over 2 times the time is 5. So S equal to 25 over 2 times 5. So that's 2.5. So 2.5 times 25, that's S equal to 25 times 25 is 625. So 62.5. Yes, 62.5 meters. All right. Then let's go to number 3. Number 3 question says, number 4 rather. Number 4 question says that a car starts from rest. Number 4, a car starts from rest. U is 0. That's the first thing I'm writing. Is that clear? And acceleration formula at that. So the acceleration is 25 meters per second squared. For 30 seconds, time is 30 seconds. What distance does it cover in the 17th second? So what distance does it cover in the 17th second? This distance is the distance between its 16th second of motion to 17th second of motion. This is the 17th second. From 16 to 17 is the 17th second. The 1 second between 16 and 17. Is it clear now? So since the body traveled from rest, our formula S becomes 1 over 2AT squared. No, I know what to use directly. Do you see A and T? So S is what we're looking for now. Now, but the time is different now. Watch. Look at the way I'm going to approach that. There are two ways of solving this. Let me show you the first way. The first way is to calculate the distance traveled in the 17 for 17 seconds and the distance traveled for 16 seconds. Then subtract them. You see that we'll get the same answer. But I'll now show you the fastest way. So distance for 17 seconds, that will be s equal to 1 over 2 times a, which is 25, times the 17 seconds. Time is now 17 seconds, so 17 squared. So s equal to, Jesus, we need calculator. What is 17 square? Oh, that is 289. 289. Calculator. 289 times 25. 25 times 289. Let's quickly do it. Let's do it. 289 times 25. So 5 times this is 45. 4. This 4. That's 44. This times this 14. 2 by this 18. 1, 17, 1, 5. So we have 5, 2, 2, 7. So the distance traveled in the 17 second, S17, is 7225 over 2. Remember that this 2 is still there. So divide it. 2 here 36, 2 in 25, 12.5. So our answer is 3612.5. This is the distance traveled in 17 seconds. In 16 seconds, S16 will be what? 1 over 2, 80 squared still, with time being 16 now. That will go to 1 over 2 times A, which is 25, times 16. Someone is now asking, what are you now using this guy to do? 16 squared. Calm down. Sometimes I'll be given to confuse you. So T squared, 16 squared. So 16 squared, 256. Half of 256. Half of 16 squared is 128. So we now have 128 times 25. 128 times 25. Let's do 128 times 100. That's this, divided by 4. Is that clear? So that will be, that's what I was supposed to do here still. So 4 here, 3, but it's easier here. 4 here, 200. So the answer is 3,200 here. Just use your own calculator, you get it. So S16th, 17th second will be equal to S17 minus S16. What is S17? 3612.5 minus 3200. So this becomes 200 minus this. That's 412.5. That's the answer, meters. That's the distance traveled in the 16th second. But let me show you the fastest way. The fastest way is just do this. It's just to do this. Come here and say that S equal to, you know that S is already 1 over 2. A, now this is your T square will now be 16 squared, 17 squared minus 16 squared. So that becomes 1 over 2 times A times 25 times 17 squared, 289 minus 256. Subtract 1 over 2 times 25. This becomes times 33, yes. So 25 times 33, that will be 3,300 divided by 4. Divide by 8 again. Divide by 2 again. So here, 32.8. It's not giving. Let's do it. 32.8. Remainder 1. 4 in 10. 2 remainder 2. 4 in 20, 5. So divide this by 2. In 82, 41. Yes, 412. Did you see that? 412.5. What did I do here? I subtracted the first time squared minus the second time squared. So that's the fastest way. Alright, before the power goes off, Let me quickly show you for vertical motion. Now, it's not much that is happening here. It's just the equation transformation that students don't understand. Now, watch me. Now, for vertical motion, let your attention be on this side of the board now. I don't want to start wasting time again. For vertical motion now, vertical linear motion. What does vertical linear motion mean? That is, when you throw a body upward, or a body is dropping from a height, throw a body upward, or a body is dropping from a height. If a body is thrown upward, what will happen? So there are two types of vertical motion, upward and downward linear. So that is, the body is falling, that's downward linear. Upward linear, you throw the body up. If you throw a body up, listen, the transformations that happen to the equation now. First, we call S becomes H, height. Exactly. That's the first thing that transforms. Then the body will not accelerate by itself again. Acceleration will become acceleration due to gravity. But in this case, when a body is going upward, acceleration actually becomes minus G. Why? In which direction does gravitational force pushes a body, accelerates a body? Downward. That's the natural state, natural condition of acceleration in gravity, pushing downward, coming downward. But now you are throwing something up. So that thing will accelerate with negative G. You see, power is out. So let's just quickly finish this. When the body is going up, A is minus G. When the body is coming down, A is G, because it's following the direction of gravity, associated gravity, which is down. All right, so let's look at the transformations that happen. S will become H, so this one doesn't really change. But no, there's another thing. When you throw a body up, the body will go up and stop somewhere before dropping. So V is always 0. Final velocity when the body is going up is what? 0. Final velocity when the body is going up is what? 0. So it means the velocity will only be U. Is that clear? So let's start with this. Let's start with the S. S becomes H equal to, when the body is going up, V will be 0. So that will be U over 2 times T. You see the transformation that has gotten here, has happened here. The second equation, that's for this one, that's for this one. That's for that one. For the second equation, V equal to U plus AT, to transform to, when the body is going up, V is 0. So U is the one that has value there. So 0 is equal to U. Now, A is there, A is minus G, minus GT. Make sense? So U becomes GT. This one, now, that V is 0 at maximum height. So this one is velocity at maximum height. So this equation is for at maximum height. But at a given height, the body will still have velocity, even though it will be low. So at a given height, this one is at maximum height. At a given height, V will be equal to U minus GT. That's to show you that V will be lower. Exactly. If you subtract this thing from U, it means V is lower. So that is at a given height, at a given distance above, height above. Okay. Now let's look at the next equation. H becomes UT minus, because A is now minus G, minus 1 over 2 GT squared. That's another transformation when the body is going up. Remember, don't forget this one. I said that O is only 0. Okay, sorry. Here for this place too, H will be equal to V plus U over 2 at a given height. This one is also at a given height. But at maximum height, this is what you transform to, at maximum height. Then the last one, at maximum height, V is also 0. So 0 squared equal to U squared minus 2G, S is now H. So this is what will happen. So at maximum height, this guy will come here, U squared will be equal to 2GH. This is the transformation. But at a given height, comma, our v squared becomes u squared minus 2gh. Still showing you that u would have reduced in its value because velocity reduces as the body goes up. Don't forget, as the body goes up, velocity reduces. As the body comes down, what will now happen? Velocity increases. That's why you see that the body, when it's traveling down, is when it hits the ground that it sounds the loudest. Boom! Because the momentum has increased because of the velocity has increased. Make sense? Good. Alright, so let's quickly finish this off. I'm stopping here. You should by yourself be able to apply these guys to solve equations. I'm stopping because of the light. It's not really as good as before. So what will now happen is that I'll post my video on projectile. That's where we're supposed to get to. I'll link it in the description so that you can watch it. Okay, so please do well to watch it. And please, it took a lot of time to shoot this video. Like I've been shooting for more than 2 hours, almost 2 hours now. Almost 2 hours going back and forth. So please do well to subscribe. That's what I'm just saying. Subscribe, okay? God bless you as you do so. All right, let's go. Now, when the body is going downward, A is G. So our equation becomes at a given height. In fact, when the body is going downward, it is U that might be zero. That might be zero because if the body was falling before our reference, the body's U will not be zero. But if it starts to fall when we reference it, U is also zero. It starts to fall from rest. So H will be equal to V plus U over 2T. It didn't change. But yeah, for this one, V will be equal to U plus GT. For here, for this guy, H will be equal to UT plus half GT squared. Is this clear? Then for this case here, V squared will be equal to U squared plus GT plus GT. Plus 2GH plus 2GH. Alright, so this will be it for this video. If you now want me to solve questions on this, put it in the comment section. I promise you I'll solve questions. God bless you as you subscribe to the channel.